Hello friend, today we are going to learn the Routh procedure. It has been remarked that the Hamiltonian formulation is not particularly helpful in the direct solution of mechanical problem. Often we can solve the 2n first order equation only by eliminating the sum of the variable. For example, the p variable, which is speedily lead back to the second order Lagrangian equation of motion. But an important exception should be noted. The Hamiltonian procedure is specially adapted to the treatment of problem involving the cyclic coordinate. Let us consider the situation in Lagrangian formulation when some coordinates, say qn, is cyclic, means this qn coordinate is cyclic. The Lagranges as a function of q and q dot can be written as L is equal to L of q1 q2 up to qn minus 1 and q1 dot q2 dot up to qn dot t. That is the Lagranges as a function of q and q dot. All the generalized velocities still occur in the Lagranges, and in the general will be function of time. We still have to solve the problem of n degree of freedom, even though the 1 degree of freedom correspond to cyclic coordinate, and cyclic coordinate in Hamiltonian formulation, on the other hand, truly deserve its alternative description as ignorable. For in the same situation, Pn is some constant alpha, and h is the form of h is equal to h of q1 q2 up to qn minus 1 and p1 p2 up to pn minus 1 alpha t. In effect, the Hamiltonian now describe the problem involving only n-1 coordinate, which may be solved completely ignoring the cyclic coordinate except as it is the manifested in the constant of integration alpha to be determined from the initial condition. The behavior of cyclic coordinate itself with time is then found by integrating the equation of motion, that is qn dot is equal to del h upon del alpha. The advantage of the Hamiltonian formulation in handling the cyclic coordinate may be combined with Lagrangian covariance for non-cyclic coordinate by the method devised by Routh. Especially, we carry out the mathematical transformation from q and q dot basis to q and p basis only for those coordinates that are cyclic, obtaining their equation of motion in the Hamiltonian form, while the remaining coordinates are governed by the Lagrange equation. If the cyclic coordinates are labeled qs plus 1 to qn, then new function r may be introduced defined as r of q1 q2 up to qn, second q1 dot up to qs dot, and third ps plus 1 up to pn, and t is equal to summation of I is equal to s plus 1 to n pi qi dot minus L, that is equation 1, and which is equivalent to write the R of Q1 Q2 up to Qn, second Q1 dot up to Qs dot, and Ps plus 1 to Pn, and time t is equal to S cyclic to Ps plus 1 to Pn minus L non-cyclic Q1 up to Qs, second Q1 dot to Qs dot, that is equation 2. It is easy to show for the S non-integrable coordinate, then the Lagrangian equation is given as d upon dt into del r upon del qi dot minus del r upon del qi is equal to 0, where I is equal to 1 to S. This is equation number 3. Are satisfied while for the n minus 1 ignorable coordinate. The Hamiltonian equation apply as del r upon del qi is equal to minus p I dot is equal to 0, and del r upon del pi is equal to qi dot, and I is equal to S plus 1 to n. That is equation number 4. A simple, almost trivial example may be clarify Routh procedure and the physical significance of quantities involved. Consider the Kepler problem investigated, that of the single particle moving in the plane under the influence of the inverse square center force F of r derived for the potential V of r is equal to minus k upon r raised to the power n. Then Lagrangian is given by L is equal to m by 2 r dot square plus r square theta dot square plus k upon r to the power n. As noted before, the ignorable coordinate is theta. This theta is ignorable coordinate, and if the constant conjugated momentum is denoted by pq, the corresponding Routhian is given by r of r dot p theta is equal to p theta square upon 2m r square minus 1 by 2 m r dot square minus k upon r to the power n. Physically, we see that the Routhian is the equivalent one-dimensional potential v dash of r minus the kinetic energy of the radial motion. Applying the Lagrangian equation to the non-cyclic radial coordinate r, we obtain the equation of motion r double dot minus p theta square upon m r raised to the power 3 plus n k upon r to the power n plus 1 is equal to 0, and applying the Hamiltonian equation to the cyclic variable theta, we obtain the pair of equation, that is p theta dot is equal to 0 and p theta upon m r square is equal to theta dot. and whose solution is p theta is equal to m r square theta dot is equal to L is equal to constant. And typically, the Routh procedure does not add to the physics of the analysis presented earlier, but it makes the analysis more automatic. In complicated problem with many degree of freedom, this feature can be considerable advantage, and it is not surprising. Therefore, the routine procedure find its greatest usefulness in the direct solution of problem relating to engineering application. But as a fundamental entry, Routhian is the terrestrial hybrid combining some of the features of both the Lagrangian and Hamiltonian picture. Thank you.